Hi, Chris Kuzmal here. Today we're going to talk about Riemann sums. So a Riemann sum is an approximate of an integral of a function, of a definite integral. And broadly speaking, the idea is we're going to sum up a bunch of f's of x's where we compute at every sequence in a step. So f of x, f of 0 plus f of dx plus f of 2 dx plus etc., all the way up to f of n minus dx plus f of n. And that's all multiplied by dx. And that is effectively what we call a sum of rectangles, which is the integral of f is approximately the integral of f from 0 to n. There's refinements of this approximation called the trapezoidal and midpoint methods. But for most scientists and engineers, this basic approximation is good enough. If you're a numerical analyst, a control theorist, a control engineer, then the refinements can be of great interest. And one of the most common examples I'm aware of is something called a Runge-Kutta method. So you can go there if you want. Uh, let's talk about some of the specifics then, just so we're familiar. The left sum method conceptually takes a sequence of rectangles and looks at the left values of the function as we evaluate it. And an example would be if f of x is the sine of x, our dx was 0.1, and the number of samples that were number of places we evaluate is 6, and they're each separated by 0.1. Then, first of all, the integral of sine x from 0 to 0.6 is precisely negative cosine of 0.6, which is the derivative of the sine of x evaluated at 0.6, minus negative cosine of 0, and that computes out to approximately 0.1747. I mean, it's exactly 0.1747, followed by an infinite number of additional digits, which I won't put down here. We can approximate this as the sine of 0 plus the sine of 0.1 plus the sine of 0.2, sine of 0.3, 0.4, 0.5, which is using the left-hand rule because we didn't do the 0.6, we just started with the 0. And then, well, that's 1.4628, which isn't quite right. We have to multiply by the width of 0.1. So the actual sum is 0.14628, which is pretty close to 0.1747. Likewise, the right-hand sum conceptually is the right-hand rectangles. And everything here is pretty much identical, except we're computing sine of 0.1, 0.2 instead of sine of 0.1, and we're including the sine of 0.6. And that sum adds up to 2.0274, which we multiply by 0.1 and come up with a pretty close result. Well, it turns out that if you average the right sum and the left sum, that's the trapezoidal sum. Oops. And so the average of the right sum and the left sum, I keep going back and forth, I apologize. The average of the left sum and the right sum is what the trapezoidal rule gives, and it turns out that that is a more precise measure. The midpoint sum is a little bit confusing, though, because it's not sampling at the same points typically that you think of if you're sampling the same number of points for the trapezoidal rule, the left or the right summation rule. So it's better, I think, to look at actual computer code that does each of these. And that's, I think, going to make it even clearer. And we'll do that in the next video.